In the previous class, we have learnt about quantization. We have also studied the design process for a uniform quantizer when the input source has uniform probability density function. However, in practice, quite often we come across input sources which have non-uniform probability density function. In such a case, if we still desire the simplicity of a uniform quantizer and obtain the step size based on the earlier procedure, that is dividing the input range by the number of levels of quantizer, then this design is not a very good one. In order to understand this concept more clearly, let us take an example. Let us assume that the input range is minus 100 to plus 100, and let us also assume that the input falls in the interval minus 1 to plus 1 with probability 0.95, and it falls in the interval minus 100 minus 1 100 with probability 0.05. Now, let us design 8 level uniform quantizer. Now, if we follow the procedure which we discussed in the earlier class and obtain the step size, that is delta, as the input range, that is 200, divided by the number of levels of the quantizer, that is 8, we get equal to 25. What this implies, that the inputs in the interval between minus 1 to 0 will be represented by the value minus 12.5, and the input in the range between 0 and 1 would be represented by plus 12.5. So, on the real axis, we can denote the decision boundaries and the reconstruction levels as shown here. Now, the blue ones are the reconstruction levels and the black ones are the decision boundaries. So, the maximum quantization error that can be incurred is 12.5. However, at least 95% of the time, the minimum error that will be incurred will be 11.5, because the input lies between minus 1 to plus 1 with a probability of 0.95. Now, obviously, this is not a very good design. So, a much better approach would be to use a smaller step size, which would result in better representation of the values in the range -1 to +1 interval, even if it is meant a larger maximum error. So, based on this idea, suppose we pick step size of 0.3. Now, based on this step size, the reconstruction levels would be as follows: minus 1.05, minus 0.75 up to plus 1.05. Now, and these are the decision boundaries, where the extreme ones are minus 100 and plus 100. Now, in this case, the maximum quantization error goes from 12.5 to 98.95, that is when the input is plus 100 and the reconstruction level is 1.05. However, 95% of the time the quantization error will be less than 0.15. Therefore, the average distortion or the mean squared quantization error for this quantizer would be substantially less than the earlier quantizer. So, the conclusion is that when the source PDF is not uniform, it is not good idea to obtain the step size by simply dividing the input range by the required number of quantization levels. And this approach becomes totally impractical when we model our sources with probability density functions that are unbounded, such as Gaussian PDF. Therefore, somehow we must include PDF in the design process of a quantizer. So, our objective is to determine the step size that for a given value of L, that is number of levels of quantizer, will minimize the mean squared quantization error. Now, the simplest way to achieve this is to write the distortion as a function of the step size. So, we should be able to write the distortion as a function of step size and then minimize this function with respect to the step size. Now, an expression for the minimum squared quantization error for an L level uniform quantizer as a function of delta can be found by replacing the boundary and the reconstruction level in the following equation. Now, this is the mean squared quantization error as a function of reconstruction level and decision boundaries. So, we should replace the decision boundary, that is Bj's, and reconstruction levels Yj by functions of delta. Now, as we are dealing with a symmetric condition, we need only compute the mean square quantization error for positive values of x. The mean square quantization error for negative values of x will be the same. So, for a uniform mid-rise quantizer, the decision boundaries are integral multiples of the step size delta, and the representation level for the interval I minus 1 delta to I delta is given by 2 I minus 1 upon 2 times delta. Therefore, based on this, the minimum squared quantization error can be rewritten as shown here. Now, this expression is function of delta. Therefore, to determine the optimal value of delta, we can take a derivative of this equation with respect to delta and set it equal to 0. So, if we do that, this is the expression which we get. Now, in order to derive this expression, we have to use the Leibniz rule, which states that if A x and B x are monotonic, then differentiation of this expression is given on the right hand side. Using this Leibniz rule, we get the following expression. Now, this is a rather messy looking expression, but given the probability density function, that is PDF, it is easy to solve this equation using any one of a number of numerical techniques. The following table lists step sizes found by solving the previous expression for 9 different alphabet sizes and 3 different probability density functions. Now, the results given in this table are taken from these 2 papers. One is by Max and other is by Adams and others, which had appeared in IRE transaction on information theory and IEEE transaction on communications respectively. We will return back to the discussion on the results depicted in this table, but before that, it is important to know that in practical situations, the inputs are always bounded, and it is only a mathematical convenience that we model the non-uniform sources with unbounded support. Now, if the input is unbounded, then this implies that the quantization error is no longer bounded either. So, the quantization error as a function of input is shown in the following figure. Now, from this figure, we see that in the inner intervals, the error is still bounded by delta by 2. However, the quantization error in the outer intervals is unbounded. Now, these two types of quantization error are given different names. The bounded error is called granular error or granular noise, while the unbounded error is called overload error or overload noise. In the expression for the minimum squared quantization error, the first term represents the granular noise and the second term represents the overload noise. Now, the probability that the input will fall into the overload region is called the overload probability. So, if we assume that the input has probability density function as depicted here, then this region denotes the overload probability and the region here denotes the granular probability. Now, as depicted here, the non-uniform sources usually have probability density function, that is PDF, that are generally peaked at 0 and decay as we move away from the original. Therefore, the overload probability is generally much smaller than the probability of the input falling in the granular region. Now, from this equation, it is clear that if we increase the step size delta, this will result in an increase in the value of L by 2 minus 1 times delta, which in turn will result in decrease in the overall overload probability and therefore, the overload noise. However, an increase in delta will also increase the granular noise, which is the first term in this equation. So, the design process for the uniform quantizer is a balancing of these two effects. An important parameter that describes this trade-off is the loading factor FL, which is defined as the ratio of the maximum value the input can take in the granular region to the standard deviation. And a common value of the loading factor is 4, and this is also referred to as 4 sigma loading. Now, we have also studied that when quantizing an input with a uniform PDF, the SNR and the bit rate are related by this equation. What this equation states is that for each bit increase in the rate, there is an increase of 6.02 dB in the SNR. Now, coming back to the earlier table, this table shows that although the SNR for the uniform PDF follows the rule of a 6.02 dB increase in the SNR for each additional bit, this is not true for the other PDFs. And it is also evident from this table that the more peaked a PDF is, that is the further away from the uniform PDF it is, the more it seems to deviate from the 6.02 dB rule. We also concluded that the selection of the step size is a balance between the overload and granular noise. Now, this is a PDF for the Laplacian. The Laplacian PDF has more of its probability mass away from the origin in its tail than the Gaussian PDF. So, what this implies is that for the same step size and the number of levels of quantizer, that is L, there is higher probability of being in the overload region if the input has a Laplacian PDF, then if the input has a Gaussian PDF. So, this implies that for the same number of quantization levels, if we increase the step size, then the size of the overload region is reduced, and hence the overload probability decreases at the expense of increase in the granular noise. Therefore, what it implies that for a given L, if we calculate the step size to balance the effects of the granular and overload noise, then PDFs that have heavier tails will tend to have larger step sizes. Based on this argument, this table shows this effect. For example, for 16 levels, the step size for the uniform PDF is 0.217, whereas for the same alphabet size, the step size for the Gaussian PDF is 0.3352, whereas for the Laplacian PDF it is still larger, it is 0.4609. So, if the input distribution has more mass near the origin, then the input is more likely to fall in the inner levels of the quantizer. Now, if we recall our design procedure for lossless compression schemes, where we had tried to minimize the bit rate or the average number of bits per input symbol, we had followed a strategy of assigning a shorter code words to symbols that occurred with higher probability and longer code words to the symbols that occurred with lower probability. So, in a similar manner, in order to decrease the average mean square quantization error, we can approximate the input better in regions of higher probability, perhaps at the cost of worse approximation in regions of lower probability. Now, in order to achieve this, we can assign smaller quantization intervals in those regions that have more probability mass. So, if the source distribution is like the distribution shown here, we would have smaller intervals near the origin. So, if we wanted to keep the number of intervals constant, this would mean that we have larger intervals away from the origin. So, a quantizer that has non-uniform interval is called a non-uniform quantizer. An example of a non-uniform quantizer is shown in this figure. Notice that the intervals closer to 0 are smaller, hence the maximum value that the quantizer error can take is also smaller in this region, and that is why there is a better approximation. Now, we pay for this improvement in accuracy at lower input levels by incurring larger errors when the input falls in the outer intervals. Now, since the probability of getting smaller input values is much higher than getting larger signal values, on the average the distortion will be lower than if we had a uniform quantizer. So, while a non-uniform quantizer provides lower average distortion, the design of a non-uniform quantizer is also somewhat more complex. So, the basic idea is quite straightforward. Find the decision boundaries and reconstruction levels that minimize the mean squared quantization error. Now, let us look at the design of such a non-uniform quantizer in more detail. So, if we have a probability model for the source, then a direct approach for designing the best non-uniform quantizer is to find the bj's and yj's that minimize this equation. Now, to obtain bj's and yj's, we can follow the following procedure. Setting the derivative of this equation with respect to yj to 0 and solving for yj, we will get the following expression. What this expression suggests is that the output point for each quantization interval is the centroid of the probability mass in that interval. Similarly, taking the derivative of mean square quantization error with respect to bj and setting it equal to 0, we get an expression for bj as follows. And this expression suggests that the decision boundary is simply the midpoint of the two neighboring reconstruction levels. Solving these equations will give us the values for the reconstruction levels and decision boundaries that minimize the mean squared quantization error. Unfortunately, to solve for yj, we need the values of bj and bj minus 1, and to solve for bj, we need the values of y j plus 1 and y j. In 1960, Lloyd-Max showed how to solve the two equations iteratively in this paper. Now, the same approach was discussed by Stuart P. Lloyd in a 1957 internal Bell Labs memorandum and was published little later in 1982. So, both the approaches are same. Therefore, the algorithm which is used to solve the two equations iteratively is known as Lloyd-Max algorithm. So, Lloyd-Max algorithm works as follows. Suppose we want to design an L level symmetric mid-rise quantizer Now, to define our symbols which we will be using for derivation, let us use the following figure. From the figure, we observe that the design of this quantizer needs to obtain the reconstruction levels y 1, y 2 up to y L by 2. So, and the decision boundaries B 1, B 2 up to B L by 2 minus 1. The example here is for L equal to 8. The reconstruction levels y minus 1, y minus 2 up to y minus L by 2 and the decision boundaries B minus 1, B minus 2 up to B minus L by 2 minus 1 are obtained via symmetry. The decision boundary B 0 is 0 and the decision boundary B L by 2 is simply the largest value the input can take, and for the unbounded input this would be infinity. So, in this equation let us set j equal to 1. If we set j equal to 1, we get y 1 is equal to b 1 b 0 x p x dx by integral over b 0 to b 1 p x dx. As b 0 is known to be 0, we have two unknowns in this equations b 1 and y 1. Now, we make a guess at y 1 and later we will try to refine this guess. Using this guess in this equation, we numerically find the value of b 1 that satisfies this equation. Now, setting j equal to 1, in this equation and rearranging the terms slightly, we get y 2 is equal to 2 b 1 plus y 1. So, from this we can compute y 2. Now, this value of y 2 can be used in this equation with j equal to 2 to find b 2, and which in turn can be used to find y 3. We continue this process until we obtain a value for y 1, y 2 up to y L by 2 and decision boundaries b 1, b 2 up to b L by 2 minus 1. Now, the accuracy of all the values obtained to this point depends on the quality of our initial estimate of y 1. Now, we can check this by noting that y L by 2 is the centroid of the probability mass of the interval b L by 2 minus 1 and b L by 2. We know b L by 2 from our knowledge of the data. Therefore, we can compute the integral y L by 2 is equal to and compare it with the previously computed value of y L by 2. Now, if the difference is less than some tolerance threshold, we can stop, otherwise we estimate the value of y 1 in the direction indicated by the sign of the difference and repeat the whole procedures. Now, this table provides the decision boundaries and the reconstruction levels for various probability density functions and number of levels generated using the procedure just discussed. Notice that the input distributions that have heavier tails also have larger outer step sizes. However, these same quantizers have smaller inner step sizes because they are more heavily peaked. The SNR this table shows the decision boundaries and the reconstruction levels for various probability density functions and number of levels generated using the procedure just discussed. Notice that the distributions that have heavier tails also have larger outer step sizes. However, the same quantizers have smaller inner step sizes because they are more heavily peaked. The SNRs for these quantizers is also listed in this table. Now, if we compare these values with those for the PDF optimized uniform quantizer, we can see a significant improvement, specifically for distributions further away from the uniform distribution. Now, this non-uniform PDF optimized quantizer is also known as Lloyd-Max Quantizer. This quantizer has a number of interesting properties. We will not go into the proof of this property, but for the sake of completion they are stated here. The first property says that the mean values of the input and output of a Lloyd-Max quantizer are equal. The next property says that for a given Lloyd-Max quantizer, the variance of the output is always less than or equal to the variance of the input. Third property says that the mean squared quantization error for a Lloyd-Max quantizer is given by the following expression, where the first term, that is sigma x squared, is the variance of the quantizer input, and the second term is the second moment of the output. So, if the input has 0 mean, then this is the variance of the output. The fourth property says that if n denotes the random variable corresponding to the quantization error, then for a given Lloyd-Max quantizer, expectation of the random variable x and n is equal to minus sigma q squared. And finally, for a given Lloyd-Max quantizer, the quantizer output and the quantization noise are orthogonal. What it means that expectation of the quantizer output and the quantizer noise given the Lloyd-Max quantizer, that is the decision boundaries, this is equal to 0. Now, the proofs for these properties can be found in the following references. The first two references had appeared in IEEE Transaction on Information Theory, and the last references is in the Eurosip Journal of Signal Processing. It is important to remember that while designing both uniform and non-uniform PDF optimized quantizers, it is essential to know the input source probability density function and the parameters associated with this PDF. For example, in this table which we saw earlier, the values were obtained under the assumption of either Gaussian PDF or Laplacian PDF, and it was also assumed that the input PDF have 0 mean and unit variance. But now, in a practical scenario, it is strictly not necessary that the actual input source behaves as the one assumed while designing the quantizer. Now, the two most important types of mismatch which can occur are as follows. First, the actual input probability density function matches with the PDF assumed during the design process, but the variance of the actual input process does not match with the variance assumed in the design process, or the actual input source probability density function itself does not match with the PDF assumed in the design process, and the variance of the actual input source matches with the variance assumed in the design process. Now, there are different methods to overcome these problems, and this have been extensively discussed in the literature under the topic of adaptive quantization, which we will not discuss in this class. Now, the Lloyd-Max quantizer is an optimum quantizer as far as minimization of mean squared quantization error is concerned, but the implementation of a Lloyd-Max quantizer is far more complex than a uniform quantizer because of unevenly spaced decision boundaries. The very basic principle on which the design of a Lloyd-Max quantizer is based is to provide small size quantization intervals in the regions where the input has high probability. Therefore, another approach to the design of a quantizer which exploits the input PDF would be to expand the region in which it lends with high probability in proportion to the probability with which the input lends in this region. We will investigate this approach in much more detail in the next class.